Hey guys, and welcome to a video on solving inequalities algebraically. Let's do this! Before we start solving inequalities, let's recall that when we were solving equations before, we had some properties of equality that were really helpful to us. First being the additive property of equality, which said if we had an equation where two quantities were equal to one another, we could add or subtract any number to both sides of the equation, and the equation would remain true. We also had the multiplicative property of equality, which said if we have an equation where two quantities are equal to one another, we could multiply or divide both sides of the equation by any number, and the equation would remain true. And those were really necessary for us to solve all sorts of tough equations that we've dealt with already. But now we're dealing with inequalities, where we have two quantities that are not necessarily equal to one another. One is bigger than the other, or one is perhaps smaller than the other. So let's start an investigation to see if these properties hold when we're dealing with inequalities. So let's start with two inequalities that we definitely know to be true. The first being 5 is greater than 2. Definitely true. The second being -7 is less than or equal to -3. Also true. Let's see what happens if we add or subtract a number from both sides of the inequality. So let's try adding 12 to both sides of each of these inequalities and subtracting 4 from both sides of these inequalities and see what happens. In all four cases, it appears that adding or subtracting a number gave us an inequality that still remained true. And this leads us to our first property of inequalities, that if we have an inequality where one quantity is bigger than another, or one quantity is smaller than another, we may add or subtract any number we like to both sides of the inequality, and that inequality will still be true. And if you look at the ones right in front of us, you could add or subtract any number you want to any of those inequalities, and they will still remain true, and I urge you to try that. So let's use these properties of inequality to solve some inequalities with variables in them. So in the first inequality, d minus 5 has to be greater than or equal to 3. Now first, I want to appeal to our intuition. I hope it's clear that if d were exactly equal to 8, that would be the smallest number that would make this statement true. D could be anything greater than 8, or 8, but nothing less than 8, or that number minus 5 would be too small. So we know the solution to this inequality is going to be any number greater than or equal to 8. But I want to show that we can use that additive property of inequality to solve this inequality algebraically and say, well, given an inequality, we may add the same number to both sides of the inequality, and we will end up with a new true inequality. So using both intuition and algebraic skills to solve that inequality. For the second example, we know that if w were -14, that would just be too big, because -14 plus 11 is exactly equal to -3, but we need this to be less than -3. So if w were anything less than -14, we would end up with a true statement. Well, using some algebraic maneuvers, we can obtain that same result by subtracting 11 from both sides of that original inequality, and we end up with another true inequality, which happens to be our solution set. So now that we know we can add or subtract any number to both sides of an inequality, and it will remain true, what happens if we multiply or divide both sides of an inequality? Is it still going to remain true? Let's start by multiplying and dividing by positive numbers. So here are our familiar inequalities again, and let's multiply both sides of each of these inequalities by 3. Let's divide each side of both of these inequalities by 8, and we'll multiply each of them by 24. And let's see if we continue to get true statements. Well, in all 6 examples, it appeared that if we multiply or divide both sides of the inequality by a positive number, our inequality remained true. So let's investigate a couple examples. In the first one, 1/4 times m is greater than or equal to 9. And first, I want to appeal to our intuition. Perhaps we can tell that the smallest number that m could possibly be is 36. If m were exactly equal to 36, 1/4 times m would be exactly equal to 9. M could of course be anything greater than 36 as well. So we already know the numbers that make that statement true are those that are greater than or equal to 36. But now I want to show us how we could obtain that same solution algebraically. Well, we know we can multiply both sides of this inequality by a positive number and it will remain true. So let's multiply both sides by 4. Of course, the 4 and the 1/4 will multiply to give us 1, and we just end up with this statement right here. So we can use intuition and algebraic maneuvers. In our second example, 7 times g is less than 42. We know that if g were exactly equal to 6, then 7 times g would be equal to 42. So g needs to be anything less than 6. Well, now we've kind of solved this inequality using our intuition. How could we solve it using algebra? Well, we know we may divide both sides of this inequality by a positive number and obtain another true statement. So let's divide both sides of this inequality by 7. These 7's cancel out, and we end up with the statement g is less than 6. You could have multiplied both sides of that inequality by 1/7 if you wanted, but just showing how we can use algebraic maneuvers and intuition to solve these inequalities. Now, what happens if we have an inequality and we start multiplying or dividing both sides by a negative number? Well, let's start with the easiest negative number, -1. So let's start by just multiplying each of these inequalities by -1, and let's see what happens. Very interesting. Let's look at our first example. When we originally had 5 is greater than 2, and we multiplied both sides of the equation by -1, we ended up with two numbers for which we would have to switch the direction of the inequality to make this statement remain true. So that's interesting. When we multiplied by -1, we had to switch the direction of that inequality. Let's take a look at the second example. We started with -7 is less than or equal to -3, which is a true statement. When we multiplied both sides by -1, we ended up with two numbers for which we would need to change the direction of that inequality to make it remain true. So in both of these examples, multiplying by -1 made us have to switch the direction of our inequality to keep it true. Let's try a couple more examples with negative numbers. Let's multiply both sides of these inequalities by -12, and let's divide both sides of these inequalities by -4 and see what happens. Wow! It seems that in every single example, whether we multiplied both sides of the inequality by a negative number or divided both sides of the inequality by a negative number, we had to switch the direction of the inequality sign in order to keep that statement true. And this brings us to our next property of inequality. If we multiply or divide by a negative number, then we're going to have to flip the direction of the inequality sign in order to keep that statement true. Here are a few examples that highlight this new property of inequality. So in the first, -2 times d is greater than or equal to 12, we can use our intuition to see that if d were exactly equal to -6, that would be just enough to make the statement true. If d were -7, -8, -9, etc., those would all work as well. In fact, any number less than -6 will work. So we see that the solution set to this inequality is going to be any number that is less than or equal to -6. Now, if we think about how to do this algebraically, if we were to divide both sides of this inequality by -2 in order to isolate that d, well, we would get a new statement with d on the left-hand side, -6 on the right-hand side, but we would need to make sure to flip the direction of that inequality sign. So a great way to solve an inequality with intuition and with algebra. In our second example, 8 is greater than -1/5 times k. We see that if k were exactly -40, then -1/5 times that would be equal to 8, and would be just too big. We know that if k were -39, -38, -37, those would all work. In fact, any number greater than -40 would work. So we can already see that k greater than -40 is going to be our solution set. Well, how would this work using algebra? if we wanted to isolate this k up here, we would multiply both sides of the equation by -5. And we would end up with a new inequality with a -40 on the left-hand side, just a k on the right-hand side, but since we multiplied by -5, we would need to flip the direction of the inequality. All right, now that we have some properties of inequality at our disposal, time to actually solve some inequalities. Well, what does it even mean to solve an inequality? To solve an inequality means to find values for the unknown variable, or variables, such that when you substitute those numbers in for the variables, the inequality is made true. So let's look at our first one. A plus 8 is less than or equal to 12. And I'd like you right now to pause the video and think of some numbers that would make this statement true. Now, I've written down just a few numbers that will make that statement true. And now the question is, well, how many solutions will an inequality have? Well, I think we can go on and on and on forever coming up with solutions to this inequality. So how do we capture all the solutions to this inequality? And our general strategy is to solve an inequality, take the same steps you would to isolate your variable as you would in an equation, but of course keeping in mind these slightly different properties of inequalities. So in this case, we're looking to isolate A, and I bet you know exactly how to do that. Let's just subtract 8 from both sides of the inequality. And so we find that the solutions to this inequality are any number less than or equal to 4. So how would we represent all numbers less than or equal to 4 on a number line? Well, first things first, we're going to make a point at 4 because 4 is part of our solution sets. And because we'd like to represent every number less than 4 as well, what we're going to do is we're just going to draw an arrow going to the left. And that picture right there represents every real number less than or equal to 4. Now note, if our original inequality had been a plus 8 is less than 12, and not less than or equal to 12, we're actually going to use the exact same strategy, and our graph is going to change very, very slightly. The only difference here is that we don't shade in that point right at 4, because 4 is not a solution to that original equation. We call this an open circle, and we use an open circle anytime we have a less than statement or a greater than statement. And on the left, this is what's called a closed circle, and we use that anytime we have a less than or equal to statement or greater than or equal to statement to show that that point is part of our solution set. Here are two more inequalities that are slightly tougher, but the strategy remains the same. First things first, we want to isolate a variable, keeping in mind our properties of inequality. So in the first example on the left, I think we're going to want to start by subtracting 6 from both sides. Then we're going to want to divide both sides by -2. Immediately, because we're dividing by a negative number, we're going to have to flip the direction of the inequality. And what I like to do is actually, before I forget, go ahead and do that first, so that there's no way I forget about it later. We're going to end up with A is less than -7. And to graph this on a number line, we're going to make an open circle at -7, because -7 is not a solution to this inequality, and we're going to draw an arrow to the left to represent all numbers less than -7. If the original inequality were greater than or equal to 20, then the algebra would remain exactly the same, and the graph would only change by having a closed circle instead of an open one. Here's another example, very similar to the two we just did. And what I urge you to do is pause the video, give this a try, and when you're all done, play the video and see how it went. Alright, I hope everything went well for you. And one note I wanted to make is, we flip the direction of an inequality only when we multiply or divide by a negative number, not just when we end up with a negative number. In this case, our solution set here is m is less than or equal to -5/3, and even though we ended up with a negative number here, it does not mean we needed to flip the direction of our inequality. We only divided by 3. We did not divide or multiply by a negative number. So, one last inequality for us to solve. The big difference here is now we have an inequality with variables on both sides, but the strategy remains the same. All we need to do is isolate that variable, keeping in mind the properties of inequality. So if you would please pause the video now, give this one a try, and when you're done, please play the video to see how it went. Okay, I hope that went well for you, but I wanted to make a couple of notes about this problem. You have two options here. We can either collect all of our variables on the right-hand side of the equation or collect all our variables on the left-hand side of the equation. Both are totally fine. One strategy that I like to take is, if possible, I like to collect all my variables in such a way that I end up with a positive amount of them. In this case, positive 8x. Because I know then, in that last step, I'm not going to have to switch the direction of my inequality, and it's less likely that I'll forget and make a mistake. On the right-hand side, we did have to flip the direction of the inequality. Is it a big deal? Nope, but just trying to minimize the chance for error. And one last thing that I like to point out. Some students get a little thrown off by thinking that whatever direction the inequality is pointing in, that's the direction the arrow should go in. That's not necessarily the case. I would always urge you to actually speak aloud, and for instance, in this first example on the left, say -3 is less than or equal to x, or x is greater than or equal to -3, and it's obvious that even though this inequality sign is pointing to the left, our arrow is going to have to go to the right. So this is about as hard as these problems can get, and so I hope you were able to take care of it without too much difficulty. Hey guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.